Now, to prove this result, we take a parametrization of the surface S, let R be a parametrization of S, that is R UV is X UV, Y UV, Z UV. For UV in the two-dimensional domain D. So, and we take so this is S, and this is D. This is our R. We take a parametrization of the boundary of D. So this is the boundary of D. This is R, an interval AB. The parametrization of the boundary of D is this map phi. Let phi AB map to R2 be parametrization of the boundary of D. Such that the orientation corresponding orientation of the boundary of D is positive. This means when T increase from A to B, the image of T under this parametrization phi walks around the boundary of D positively. That is, D always lies on the left side of the point. Okay. Then we know that by the definition of the induced parametrization of the boundary, this denoted by gamma, the composition of R and phi, that is AB to the three-dimensional space, that is this map. This map is gamma equal R composed with phi. This is a parametrization of the boundary of S. And the orientation is the induced orientation. That is the orientation we use to compute the line integral on the right hand side of the formula we want to prove. How to say this? The derivative is the orientation on the boundary. Okay, that is this is n given by R RU cross RV divided by the norm, and correspondingly the orientation is this. This is the derivative of the parametrization of the boundary of S. This is generated from the phi, from phi. If you fix this R unchanged, but you take another parametrization of the boundary of D, so that oriented in this way, then the corresponding orientation on the boundary of the surface, that is boundary of S, reverse. That is not the orientation consistent with the that is not the orientation induced by the chosen normal vector of S. Okay, so which this setting that is we have a parametrization of the surface, that is R, and also taken parametrization of the boundary of D, that is our phi, and correspondingly we have an orientation of the boundary of S, that is our gamma. We have gamma prime T is x prime T, y prime T, z prime T. This is precisely the composition, because gamma is the composition of R and phi. Therefore, we can apply the chain rule to see that the derivative of gamma is R prime phi T and phi prime T. Maybe we don't need this, but we state it here. Basically, we need this, but you need to know what x prime T, y prime T, z prime T is, and that is the component of this. Okay. And also P gamma T. P is a function defined on the surface. So this is P. P gamma T. Gamma is a map from AB interval to the surface, actually to the boundary of the surface, which is a part of the surface, a subset of S. And the P is defined on the surface S. Therefore, the composition is a function of T. Okay, so P gamma T, that is P tilde. P tilde UTVT. What's T tilde? P tilde. P tilde is the composition of P with gamma. So their relation is this. Here is AB interval. So here is T. T mapped to UV by phi. UV is the point on the boundary of D. Then UV R become x, y, z. And our P is a function of x, y, z. And the P tilde is the incomposition of P and R. Because x, y, z are functions of UV. Therefore, making composition of P will obtain a function P tilde. That is the composition of P and R. That is a function of UV. And of course, the composition of phi and R is our gamma. That is the relation of the variables. So P gamma T is P gamma T. This is P gamma T. Okay, P gamma T. T through P was mapped to x, y, z by gamma, and x, y, z was mapped to a real number by P. The composition is the function of T. That is also P tilde UTVT. The relation you can make the relation between the variables clear from this diagram. And also the partial derivative of P tilde with respect to U, because P tilde is a function of UV. So this by the chain rule, this is PXXU plus PYYU plus PZZU. Okay, maybe I will write p tilde here. P tilde uv is p x uv y uv z uv. Okay, so you have p tilde derivative of p tilde which is respect to u by chain law is given by the derivative of p which is respect to x, y, and z. And similarly, p tilde which is respect to v is px xv plus py yv plus pz zv. So from these two equations, we will see that p tilde u xv subtract p tilde vxu. This will give us xv maybe px xu plus py yu plus pz zu. xv subtract px xv plus py yv plus pz zv, then xu. And some terms cancels. This term cancel. The term involving px cancel. Okay, so what remains is py yx uv. That is these two terms. These two terms give you py multiplying the Jacobian determinant of yx which is respect to uv. Okay, that is determinant of yu yv xu xv. Okay, therefore the yu xv term is here. Okay, the yv xu term is here with a minus sign. So this gives us this term. And also for the term pz, similarly, you will obtain the pz zx with respect to uv. That's all. That's all what we get. Now we can complete the proof